Here begins the movie about allotropes. Here's the first slide that introduced it, related it to what you should have pulled out of your GCSE and your A-level studies. Carbon allotropes, of course, probably the most famous. Diamond, graphite, Buckminster fullerene, and then, of course, the various adaptations of that. Carbon nanotubes, moving to graphene. You're going to hear so much more about those in other modules because, of course, they're some of the most significantly new materials out there. Oxygen and ozone being those two familiar allotropes of that, and then sulfur existing in the orthorhombic form below 96, monoclinic form above 96 degrees Celsius. They both melt about 20 degrees more than that. Orthorhombic, a lot of times you'll see it called rhombic. As a crystallographer, that offends me to my core. There is a huge difference between orthorhombic and rhombic, but I guess I might have to get over that. Anyway, so let's get a little bit more detailed, and let's start off getting more detailed with sulfur. So here we have the S8 orthorhombic and the S8 monoclinic forms. They're both yellow, sometimes called alpha sulfur and beta sulfur. Well, of course, if you've got alpha and you've got beta, you've probably got gamma as well. Gamma sulfur is another form of S8, just another different way of packing those S8 puckered rings. It's called nacreous sulfur, and it's a slightly lighter yellow. Something that I puzzled about for years and years and years until I finally read a book that said it was there was, well, if you've got O2 and O3, are you going to have S2 and S3? And indeed you do. Both of them existing as gases, beautifully coloured gases. S2, blue-violet gas. S3, a cherry red gas. And both of them very, very stable at high temperatures. So I thought that was kind of cool, you know, that you do have those sulfur equivalents of oxygen and ozone. There are many other forms of sulfur. There are many other allotropes, so-called row sulfur, that exists as S8 rings. It's a nice orange-red color. They're just sort of chair formations, so nothing fancy there. So I won't draw that because I've got so many other things I can draw, starting with S7, which is another yellow form of sulfur and has this cute type ring there. Kind of looks like a weird deformed type chair. 1, 2, 3, 4, 5, 6, 7. Yes, that's for a moment I was thinking I'd only drawn 6 there. S10 rings that are yellowy green, and those, when you look at them, look like that. I think that's a pretty color too, or pretty structure. S12, again a pale yellow. This is the second most stable form of sulfur after those S8 rings. Nice historical fact. One of the greatest chemists of all time, Linus Pauling, very interested in bonding and structure. I mean, he started off most of our current theories of bonding outside of molecular orbital theory, but he also made some funky bad predictions. His most famous bad prediction was about the structure of DNA, but he also believed that sulfur S12 would exist, but it'd be extremely unstable. But as I said, it's the second most stable. Another pretty little ring, S18. It's a lemon yellow color. That's what it looks like there. And then finally, ring-wise, S20. It's pale yellow. I've drawn it like that. Oh, look at that. It's kind of gone off the edge of the screen. Anyway, maybe the movie will see it. From my view right here, you can't see what's going on to those two sulfurs. There's just 2 more sulfurs down there. It's a lot more puckered than that. It's just I was getting tired of drawing wedges and stuff, and it was hard to see it. Now, some of you, if you messed around with sulfur in GCSE or A-level, you would have melted it and then cooled it down very quickly, a lot of times just pouring it into cold water, and you would have got a yucky thing called plastic sulfur. There's actually 3 forms of what's called infinite sulfur, right? Just add written S infinity, just because there's all different possible lengths and so forth, numbers of sulfur atoms in there. Fibrous sulfur infinity is yellow and consists of just parallel helical chains together. So-called laminar sulfur, a little bit more sheet-like, again yellow, but some of those helical chains cross between themselves to give it the sheets. Then what you actually see in the lab, plastic sulfur, if you've seen it, it's kind of yucky brown that gradually becomes the yellow sulfur again, and that's a mixture of all of these chains. It's got a very ill-defined structure. Anyway, sulfur, depending on whom you read, either has the most allotropes or the second most compared to carbon, depending how you could define the various different carbon ones. I happen to think it's got some really pretty little structures there. A table, by the way, adapted from a book that first came out. I got the first edition because I'm old. Came out in the mid-80s by Greenwood and Earnshaw. One of the best descriptive inorganic chemistry books that I've ever seen. They had a second edition about 10, 12 years later. Some nice updates in it. I haven't been able to buy it yet because it was rather expensive. But a really, really good book for just giving all kinds of great details about inorganic compounds. So moving from sulfur to phosphorus. So, and you might have talked about the structure of phosphorus. I certainly expect you to know up till now that phosphorus exists as P4 tetrahedra. That's the structure that exists in the gaseous phase, in the liquid phase, and in the solid phase, white phosphorus. That's the first form of phosphorus that you get. It's a very, very reactive species. So you can see melts at 44 degrees Celsius because those tetrahedra don't pack tremendously well together. And so it has a fairly low melting point there. Extremely reactive, stored underwater because it reacts like crazy in air. Anyway, if you heat white phosphorus, you can turn it into several different allotropes. There's, again, multiple sort of weird versions of these things, but the three most important allotropes are, first of all, red phosphorus. That's what you get if you heat white phosphorus just under kind of regular type conditions, obviously not exposing it to air again. That melts at 590 degrees Celsius. If you heat it in molten lead, you get this structure here, essentially made up of these phosphorus 8 groups here, okay, that are connected by P2 groups, and then you have this group goes off to the next layer there. So a very complicated structure called violet phosphorus, again nice high melting point. Because I guess he was so weird as to think about heating up in molten lead, this is named after the chap who first did it in the 1860s, a chap called Hittorf. And then if you heat it up under high pressure, you get this black phosphorus made up of joined up cyclohexane rings, 6-membered rings here in this puckered shape, and you get these puckered sheets, and these sheets will run parallel to each other. So it's a very similar arrangement to graphite, except that these sheets are puckered instead of totally flat, which leads me on to the next slide. And that is a slide about so-called phosphorine. After the success of graphene and the wonderful applications thereof and people winning Nobel Prizes for it and all kinds of good stuff, there's been a lot of interest in making these monoatom layers, or monomolecule layers would be a better way to say it in this case, of other elements. And the same goes for phosphorine. If you take black phosphorus and you look at its layer structure, here's a nice pretty picture of the layers of it. This is looking at it from this direction, okay, and then this is looking at it from on top. You can see that if you were to get this layer here, okay, with 5.3 angstroms from that layer to the next layer, then you get this kind of picture here, which should have really phenomenal properties. And there's a lot of work been done on this so-called phosphorine. Nice little review on it in the Journal Materials Chemical C, as shown there. So we got carbon, oxygen, phosphorus, sulfur. Next one to look at is selenium, and this will actually be the last of the non-metals that we think of in terms of having allotropes. Okay, you can see the halogens don't have them, nitrogen doesn't have one, but carbon, phosphorus, oxygen, sulfur, selenium all do. So selenium fundamentally exists as Se8 rings, obviously very, very similar to the S8 rings, as you would expect, as it is in the same group as sulfur. This is often called red selenium. This is its kind of natural form. You can have this gray polymeric selenium, and then if you buy selenium, it comes as black lumps, and that's the black form. It exists as massive, massive rings, so I'm not going to try to draw those. Moving on now to the metalloids, which have some really interesting types of allotropes. First one I'm going to look at is boron. Exists as these icosahedra. I think these are just the prettiest structures there. Okay, an icosahedron fundamentally 12 borons, and next year we're going to get into a lot of the compounds that boron makes with hydrogen and carbon boranes and carboranes, and then you put metals in there and you get metallic carboranes, and they're so beautiful, and a lot of them are based around this fundamental icosahedron. Anyway, all the allotropes of boron, and there are lots of them, are based around this icosahedral structure. I'm not going to get too weird about it. I'm just going to put up this absolutely gorgeous little array here. Again, taken from a materials paper talking about things you can do with them, but you can see you have alpha rhombohedral, there's the icosahedra, there's the icosahedra here, icosahedra there, some joined fused icosahedra, 3 fused icosahedra. You can see why I didn't try to draw all these, right? And look at that one there, but all based around this fundamental icosahedral shape. Next one down will be silicon, which really exists as amorphous silicon or crystalline silicon. Crystalline silicon has a very structure that's very, very similar, if not identical, to diamond in its main fundamental structure. Looking at germanium, staying down there, you can have alpha and beta germanium. Alpha germanium is actually the less stable form of it. Exists when you cool it down, and it's germanium adopts that diamond type structure again. Beta germanium, or beta germanium, excuse me, based around not tetrahedral atoms but octahedral atoms. And so you can get this picture here. Obviously I've quit drawing bonds after a while, but every single germanium is octahedrally connected to every other germanium, so you get a nice little network there. And tin exists in those same forms. So beta tin, which is the most stable form of tin. By the way, tin's going to be the only metal that I talk about in terms of allotropes. Most metals, about 50% of metals, have allotropes, but they're just packing differences and they're boring. They're not nearly as pretty as these things are. But anyway, sorry, beta tin, octahedral shape. Alpha tin, sometimes known as tin rot, is where it takes in this tetrahedral diamond type structure. Finally, moving on to the pnictogens. We have arsenic. The fundamental form of arsenic is grey arsenic, and it again is made up of these fused 6-membered rings forming sheets. Nobody's actually talked about arsenine that I've seen. By the way, I should have mentioned that there are attempts to work with silicene and germacene, very similar to the graphene idea, trying to get those monolayers of atoms coming out. Again, you could imagine trying to do this with the arsenic. I have not seen reports, but maybe there are reports for it. Can have yellow arsenic. A lot of times people think of arsenic as being in these tetrahedral. The grey form is the fundamentally naturally found form. You heat it up in the vapor phase and it adopts these tetrahedra, very much like P4. You can also get this structure by subliming grey, or by taking the vapor and rapidly cooling it down. You can make this yellow arsenic. And you can have black arsenic that has the same fundamental structure as red phosphorus. You get this by, again, more selective cooling of arsenic vapor. And the allotropes of antimony, very, very much the same thing. You can have this antimony sheets of the fused 6-membered rings. You can have antimony 4 as a tetrahedron, or you can have these linked pseudo-tetrahedra there. So anyway, some nice little discussion of allotropes. As I mentioned earlier with tin, all metals pretty much have allotropes, or about 50% of them do, but they are just much more a difference in packing of the atoms rather than these beautifully nice bonded, covalent bonded structures that we've been seeing here. Left this slide up so you can see the pattern of the atoms, that have the elements that have these allotropes. Quite possible, of course, that ultimately they'll find allotropes of some of these other substances under weird conditions. You could almost say that the clathrates formed by noble gases that at some stage we'll discuss probably in the 3rd year could almost be defined as allotropes, but I'm not going to do that. So I hope this was fun. Again, what I want you to get out of it is the kind of pattern about it, the trends about it. You do need to know some of the fundamental things, but I'm not going to get too exacting on it, although I might ask you to draw me an icosahedron.